Hello everyone, I'm Tanya Chauhan, second year PhD student at University of Miskolc. I'm working in Department of Material Science and Engineering in Institute of Chemistry. I'm going to present my work on zirconium pillared clays and their application in wastewater treatment. Nutrient pollution. Excess amount of nitrogen and phosphorus in water body causes eutrophication. It is a state in which the surface of water body is covered with algae and plants, which further blocks the penetration of sunlight and oxygen into the water. As a result, the aquatic fauna of that water body starts dying off due to the lack of oxygen, and eventually it leads to the death of the whole water body. Phosphorus concentration greater than 0.02 mg per liter can initiate this process, and there are strict rules about the concentration of phosphorus which can be discharged into the water. According to European Commission, the concentration of total phosphorus discharged from urban wastewater treatment plant to sensitive areas is 2 mg per liter for 10,000 to 1 lakh population equivalent and 1 mg per liter for more than 1 lakh population equivalent. Also, there should be minimum 80% reduction in phosphorus concentration with respect to the load of influent. There are many methods used for phosphorus removal, such as chemical precipitation, enhanced biological phosphorus removal, ion exchange, and adsorption. Among all, adsorption is the most reliable and environment friendly. Clays have shown excellent phosphorus adsorption properties and they are good adsorbents. Structure of clays. Clays are hydrous aluminous silicates belonging to phyllosilicate family and they have particle size of less than 2 micrometer. They consist of silica tetrahedra and alumina octahedra sheets, and on the basis of arrangement of these silica and alumina sheets, they can be categorized into two types, 1:1 and 2:1. Example of 1:1 is kaolinite and 2:1 is smectite illite vermiculite. In 1:1 type, the tetrahedra and octahedra sheets they are arranged in alternate manner. In 2:1 type, one octahedra sheet is sandwiched between two tetrahedra sheets, which all together form one silica sheet, and in between these silica sheets there is presence of small cations and water molecules, and they are exchangeable in nature. Example of smectites are bentonite and montmorillonite, and we are using montmorillonite clay for our study because they have high cation exchange capacity, they are expandable in nature, and bonding between two silica sheets is weak, which permits the water and exchangeable ions to enter. Modification of clay. We are modifying our clay by using this technique called filtering or intercalation, in which the small cations like sodium, calcium, which are present in between the clay sheets, are exchanged with bulky polyhydroxy cations, and upon further heat treatment, these cations they are converted into stable metal oxide clusters, or we call them as metal oxide pillars. These new type of microporous material are termed as pillared interlayered clays or PILCs. This is the structure of pillared clay, in which two silicate layer is separated by metal oxide pillars, and thickness of one silicate layer is around 0.96 nanometer. This width of the layer along with interlayer spacing gives us the value of basal spacing. Literature review. Synthesis of inorganic pillared clays were initiated in late 1970s, and since then lot of researchers have tried to make PILCs by intercalating different metal cations, and they have used them for phosphorus, heavy metal, organic pollutant removal from wastewater. These are the properties of parent clay before and after filtering. We can see in pillared clay the interlayer spacing increases. Surface area also increases after filtering. It's around 10 times. Pore size and micropore volume also increases, and in pillared clay we get more Lewis acidity and it is more stable. We have synthesized zirconium pillared clays and we got them characterized with XRD and BET, and our future goal is to investigate different chemical, surface and structural properties of prepared PILC by using different techniques like STEM EDX, STEM, zeta potential, FTIR, etc. and to further perform phosphate adsorption test with these zirconium PILCs. We have used commercial montmorillonite for our study and we prepared sodium saturated clay in lab only. Zirconium oxychloride was used as a source of zirconium. This is the method which we used. First we saturated our clay with NaCl and then we prepared a clay suspension in which zirconium filtering solution was added drop wise and then the suspension was left for stirring for 2 hours at 50 degrees Celsius followed by aging for 24 hours at 50 degrees Celsius. Next day we washed the clay suspension and we centrifuged it and washing was done thoroughly so that all the chlorides are removed because these chlorides they prevent the formation of pillars in clay and then clay was the clay was dried in oven at 120 degrees Celsius for overnight. So in total we prepared 6 samples at 3 different zirconium to clay ratio, that is 2.5, 5 and 10C. And first 3 samples were prepared by using clay which doesn't contain sodium ions and last 3 samples 4, 5, 6 were prepared by using clay which has sodium ions. This is the XRD pattern of commercial montmorillonite which doesn't contain sodium ions and these are its modified forms. So we can see this first peak corresponding to montmorillonite at 12.5 angstrom. This is the basal spacing, and in 2.5 C this basal spacing got increased to 17 angstrom, which tells us that somewhat filtering was done, but the intensity of these peaks in all the modified samples it's very weak, so we can say that these samples they are not good enough for adsorption test. And in 5C we can see we obtained 2 small peaks which tells us that our clay structure got distorted and damaged. In 10C we can see this peak, first peak, it has basal spacing of 9.7 angstrom which is almost the thickness of one silicate layer. So it tells us that filtering is not at all happened in this sample and our clay got exfoliated. These are the XRD patterns of sodium saturated clay and its modified form. So we can see in NaCm this first peak corresponds to the montmorillonite having basal spacing of 11.42 angstrom, and in 2.5C this peak got shifted to at lower 2 theta value corresponding to higher basal spacing, that is 18.21 angstrom, which tells us that yes, filtering has been done. And in 5C again this basal spacing got increased to 18.64 angstrom and filtering is successfully done in this sample too. But in 10C we got two peaks at 19 angstrom and corresponding to basal spacing of 19 angstrom and 12.1 angstrom, which tells us that our clay structure started getting distorted when we increase the concentration of zirconium to clay. These are the specific surface area results for our clay, and we can see the surface area is we haven't achieved very good surface area. In the surface area of raw clay is 8.47 meter square per gram, and in all the samples it is less only. In literature it says that pillared clay can achieve surface area around 100 to 300 meter square per gram. So we are trying to figure out some ways through which we can increase our specific surface area of these samples. Conclusion: montmorillonite clay saturated with sodium ions shows better filtering results at zirconium to clay ratio of 5 mmol per gram. Sodium ions present in the interlayer region of the clay sheet facilitates the easy exchange with zirconium ions, which improves the pillar formation. These are the references. Thank you.